much for the invitation. And yeah, so this is some work that I did together with Francesco Kogi, who is at the Nordita in Stockholm. So I did most of the work while I was still a postdoc at the Max Planck Institute in Dresden. But for half a year now, I'm a lecturer at the University of Edinburgh. And so as a motivation for my talk, the idea is that if you do some kind of thought experiment and you're given a black box, you don't really know what is in there. And all the information you're getting from that black box is that it's making some kind of ticking noise. And it could either do something that is very irregular, like it's doing something tick, 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 or it could be something that is very precise, doing something like tick, 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 tick. And then you could ask, given just that information without knowing anything else about the black box, is there a way of saying whether one of them is alive and the other one is maybe doing just some random thermal noise? And so that's basically the question that we want to ask. And I think I was already kind of giving away the idea that the second one is doing something very precise. So you could get the impression that there is some mechanism in there that needs a battery or that needs to be fed with ATP in order to do its precise ticking. So the idea is that this would somehow cost energy to be driven, and we want to calculate these bounds on the entropy production. And that is a bit like what we have heard already before, that that's now a trend in stochastic thermodynamics to try and find better ways of inferring the entropy production. And we're not claiming that this is a very strong way of inferring it, but it is a way of inferring it that only uses a minimal amount of information. You don't need anything else other than the timing of these ticking events in order to maybe get a bound on the entropy production. So that is our motivation. And of course, there are many examples throughout biology or technology where you would have such ticking processes. So you could take something as macroscopic as a heartbeat, and you can look at the timing of that. On a smaller scale, you could look at a spike train that is produced by some neuron and look at the timing of each of these spikes. But you can also do something a bit more abstract, like you could have a protein that has two different conformations, or maybe even a blood cell that is flickering, like we heard it in Felix's talk earlier. And you could then just assign two different states, like, for example, a non-fluorescent and a fluorescent state, and you would get such a switching trajectory. And you could just go ahead and call every switch from one state to the other state that is macroscopically observable. You could call that a tick and try to get information about the system itself from that timing. And you might wonder, don't we already have the thermodynamic uncertainty relation, which you also heard about before today earlier? Can't we use already the thermodynamic uncertainty relation to get a bound or to formulate this trade-off between cost and precision? And I won't need much time to go through that again. So it's just normally you would have entropy production multiplied by a precision of some current that is always greater than 2 in units of kb. And that is exactly saying that precision costs energy. But the thing is, this does not apply to the kind of observable that we are talking about here. This kind of ticking observable is not a time antisymmetric observable that you would normally need in the uncertainty relation. And that is just because if you play the movie of that ticking box backwards, you're going to see exactly the same number of ticks when you're running backwards in time as when you're running forwards in time. So this is not this kind of observable that would be admissible to be plugged into the thermodynamic uncertainty relation. So in order to get a better insight into what's going on there, we just use a simple model again. I mean, the same broad class of model that we also look at for the thermodynamic uncertainty relation. That is just, we say that somehow in that black box, there is a Markovian network of states with some transition rates Kij. They usually would not satisfy a global detailed balance. So that means that it's somehow a driven process, and that is related to the heat. So it's related to the entropy production with the usual formula that can be evaluated in a stationary state. And now what we say is that in general, such a counting observable, every tick that you hear given off by such a black box would somehow need to be related by some internal change of state. Something must have happened when you hear such a tick. And so what we are saying is that out of the many transitions that you can take within that system, there are some that produce this kind of audible tick. And these are the ones that I color here in green. So when you have a jumper on this Markov network, whenever you cross such a green line, then you're going to hear a tick. And you can define a counting observable n of t that is just counting the number of such transitions that you had up to a certain time t. And just for classification, we distinguish basically two types of these counting observables. One of them we call flow-like. They are specific for direction. So there we would only take a jump from here to there as a tick, but not in the backwards direction. So that would not be a time symmetric observable. But we can also look at what we call a traffic-like observable. These are the ones where we count a tick in either direction. So both when you jump from here to there and back again, we would call that a tick and increment n by 1. And now to define the statistics of such a process, we basically suggest two kind of obvious measures of how you can quantify precision in such a system. So one would be if you have such a spike train, such a time series of ticks, you could just look at the time you wait from one tick to the next one. That is t star here. But that's the waiting time, and you can define the waiting time fluctuations. You take the variance of t, divide by the mean waiting time squared, and that gives you a dimensionless measure of the precision. The other alternative would be to look at what is called the Fano factor. That would rather look at the long time behavior of such a process. And there you would look at that incremental or that accumulated number of ticks n of t up to a time t, look at the variance of that. And just because of the central limit theorem, you can expect that the variance increases linearly in time. And to get something that is time independent, you would then divide that by the mean number of ticks, and then take the limit t to infinity to get this kind of long-term Fano factor. And what one can prove fairly straightforwardly is that if the system is a renewal process, that means if after every tick you're resetting the system to the same state and it loses all its memory, under this condition you can say that the Fano factor is equal to that uncertainty in waiting time. But as soon as you have some interesting correlation in your system, it's not losing all its memory, and that's basically what is most important for us, then this will not be equal, and you get a different information content from epsilon squared than you get from this Fano factor. And now to get some better insight in what's going on in that system, we were just at first doing some numerical experiments. So we are just drawing some random matrices of rates that describe random networks of states with 3, 4, or 5 states. We kept it simple at first. And then we just said that one of these edges in the network is green, so it produces an audible tick. And we look at the Fano factor just because it's kind of obvious choice. We looked at the Fano factor of the traffic through that single edge here. And that is what we plot here. For every random network that we generated, we plot that as a dot in this graph here. And the Fano factor here is plotted to the right. What we plot on the y-axis here is the cost per tick. So you would have an overall entropy production rate in that system as a whole. And that would be something that is a rate over time. To make that dimensionless, you can divide by something that an observer could also easily infer, that it's just the average rate of ticks. So that would give you the average cost per tick. And that is sigma bar here, which we plot to the top. And now it's already very suggestive from just looking at this scatter plot of these random results, is that there seems to be an accessible region in that plot, and there seems to be an inaccessible one. And what we have derived is a bound which tells you exactly where you can go in this plot and where is the forbidden region. It's that black line here. And what is kind of interesting is that this black line ends at the Fano factor 1, which basically tells you that you have no cost if you want to have a Fano factor bigger than 1, but if you want to have a Fano factor smaller than 1, you need to pay a certain cost per tick. And you might wonder what's happening really here at that Fano factor 1. And what you see is there's a very simple network with which you can saturate that bound here. And that would just be, you take just 2 states in your black box, and you have equal transition rates jumping back and forth, and every jump produces a tick. Then will just be a very simple Poisson process for the timing of these ticks. And for a Poisson process, we know that the variance and the mean is always equal. So the Fano factor would be exactly 1. But we don't have any driving force in the system, obviously. It's way too simple. You can't have any cycle that is driven. So obviously, this system here is in equilibrium. So the entropy reduction is 0. And that is basically showing that this is the one where you can get the best Fano factor if you're not prepared to pay anything. And then you can also ask for the ones where you do pay something and you get a better Fano factor than that, a smaller Fano factor. What is the optimal network that you should look at? And just by numerically optimizing that, we found that the optimal networks are always unicyclic. So it can be arranged as a ring of states. And you have a constant, or you usually have a constant driving force around that ring. That's what we indicate in this kind of energy plot as a function of state. We show that here as a constant slope. That's basically giving you that driving force. It's a non-conservative driving force, so it's always a constant downhill slope here that would be connected back into itself. And now what you see is that around the observed edge, the one that creates the tick, here we need to have a very strong biasing force, because what we want to avoid is that you have a frequent recrossing of that state. What we want to have is that the system just goes again once around the loop. That's giving it a precise timing, and then we just want to cross that once. So you need to have a strong slope here, but you cannot afford to have that strong slope everywhere in the system. That's why we use a more shallow slope here. And in the end, this turns out to be the optimal strategy. On the other hand, if you want to have, you cannot spend much entropy, if you want to have just an entropy per tick of 0.01, then the best strategy would be just what I show here in blue. And that would be to lock everything in between the 2 states between which you have the tick. That will give you basically that Fano factor 1, where you're just switching between only 2 accessible states. And that's the best you can do then. And if you want to have some kind of intermediate entropy reduction, then you would just be interpolating between these 2 extreme cases. And now the mathematical form of that bound, or the mathematical proof, it starts by looking at the current and the traffic in such a network. So the current would just be the directed flow of probability through each edge of that network. And for the traffic, we just look at the sum of the hops from left to right and from right to left. So that's a time symmetric quantity. Usually it's called T, but we found that a bit too confusing, so we just switched that to U. And now if you know for that one edge that is producing these ticks, if you happen to know the current and the traffic in the stationary state, you call that X. Then you can write down an analytic bound for the Fano factor that takes only the information X as defined here, and the overall rate or the overall entropic cost per tick in that system. And the way you prove that bound, I think there are many experts here, so I can briefly sketch that. So if you know already how to prove the thermodynamic uncertainty relation, that usually uses this kind of perturbed dynamics. And we do a very similar trick. So we just scale all the currents by a common factor zeta that is close to 1. And normally what you would do to prove the thermodynamic uncertainty relation would be to just put for all the traffics an optimal value that is determined by the given current here. But in our case, we do the same trick, but we keep the traffic for the one observed bound that is constrained by what you can see. We keep that fixed. And then in the end, we contract over zeta because we're not really interested in a bound on fluctuations in the current. And in the end, we do get a large deviation bound on that traffic-like observable. And if you evaluate that for typical fluctuations, this is the bound you get. But this is not really what we set out to do in the beginning. We wanted to have something that is independent of any microscopic insight. And obviously this X, to get this X, you would need to know more than just the timing. You would need to know what is the current and what kind of edge is it even that produces that tick. And if we want to get rid of that information, then we can just go ahead and say, well, if we don't know what X is, then let's just minimize over that and take the weakest possible bound. And that is the one that we get here. And in the end, that is now only dependent on a sigma bar. And that is what we can plot and what I have already plotted in the previous figure with the random results. So this is one of the bounds that we can derive, but we can derive a whole bunch of different bounds for slightly different scenarios. And we can arrange these different bounds that we're getting in a table like this. So we have these two different classes of observables. We can either have these traffic-like observables, these are the time-symmetric ones, or we can have flow-like observables where we don't care whether you have a tick in either direction. And then we can also have two different ways of characterizing the precision. We can have either the Fano factor or we can have the waiting time fluctuations. And we always get such a kind of bound on the Fano factor or epsilon squared, which in the end, after minimizing, which can be done numerically, or you can even try to do it approximately on paper, just minimizing over one unknown observable, you're then left with a bound that only depends on that entropy production sigma bar. And that is the kind of bounds that you get when you try to just assume that only one of these edges is green, only one of them produces a tick. But of course, you wouldn't even know that. If you just hear that ticking box, it could come from a whole orchestra of different edges in that network that are all producing their ticks, and you cannot distinguish which edge it's coming from. So you could have a system like the one I'm showing here that has two of these edges that produce ticks. They have index 1 and 2. And we can then say there is a certain contribution to the overall ticking. So the traffic or the overall tick rate would be made up of the two different contributions by how often edge 1 and edge 2 are ticking. We call these contributions the CA, and they are normalized to 1. And now for each of those edges, you would have such a quantity X, that is the traffic divided by, that is the current divided by the traffic, which of course is some microscopic information, but you can do the same trick at deriving large deviation bound that would take into account all this microscopic information for these ticking edges. And then you get a bound like this on a Fano factor. And now, of course, again, we want to get rid of all the microscopic information. So first thing we do is we substitute this quantity that always shows up here. We call, instead of xa squared, we call that just z. There is nothing deeply happening there. And then we can go ahead and so I'm plugging that z in here. And now we can just try to minimize over all these unknown quantities z. And what is coming to help us here is Jensen's inequality. So if some of these terms here are convex, then we know that by having a combination of different contributions, like you would have two different values of x and two different values of these weights C1 and C2, you could not do better than just having a single edge. And that's why we can in the end derive that the bound here, at least for the Fano factor and the traffic, is always better, or is always as good if you just have one ticking edge than if you have many ticking edges. And we tried to prove that for all the four different combinations of bound, and we found that the functions we were dealing with were in fact always convex functions, but there was one in the end that couldn't easily be proven, and that was the combination where we had the waiting time and as our observable and a flow-like observable. So we would count only jumps in one direction. And here it turns out that the function we get is indeed a non-convex one. So there it turns out that you can indeed get better precision by not just having one ticking edge, but if you have two ticking edges with different values of that quantity x, if you choose them carefully, then you can get something that is more precise than by just looking at one edge. And in the end, so this is already my kind of summary slide. These are all the 4 different bounds that we have. And at first, we had thought that the waiting time for the traffic and the flow would basically, the final factor for the flow and the waiting time for the flow would basically give the same bound. But this effect of having better precision by having 2 different values of x, that is giving us this small improvement in the bound for the waiting time of the flow compared to the final factor. So that's the small difference that you're seeing here. And yes, so that is basically how we can summarize that whole work. You can now use this information, look at any of these observables, any of these statistical measures, and either use that as a way of inferring the entropy production, or even more useful it might be if you just want to know what do I have to do in order to get a certain level of precision, then we can now tell what are the optimal networks, and we can tell you how much cost you will have to pay at least. And if you want to know more details about how this can be derived, how this can be applied, look up this preprint, and it's soon going to appear in Physical Review E. So thank you very much for your attention, and I'm looking forward to any of your questions.